Chapter 5, the periodic table. So we've talked about the periodic table a little bit, but we're going to learn some more about it and how it came about. Mendeleev was a Russian scientist, and he's the one who's gotten credit for our modern periodic table. He was looking for an order among the elements. If you think about the history of chemistry, people discovered elements, and at first they only knew a few, and then people discovered more and more elements. Now you've got all these different elements, and do you list them alphabetically, or how do you get information about them and keep them straight? So he was arranging them, trying to find patterns, and he proposed that the properties of these elements repeat at regular intervals if you order them by increasing atomic mass. He said, well, let's put them in order from smallest to largest, and then he noticed that there was common things that repeated. So, and then he arranged those into a table where the columns, what they had in common was that the formula of that element with oxygen was the same. So hydrogen, and then lithium, beryllium, boron, carbon. There's blanks here because those hadn't been discovered yet. So hydrogen and lithium and sodium all form an oxide that has the element 2O. So H2O, Li2O, Na2O, you get the idea. Over here, this column, RO2. Whatever this element is, O2. CO2, SiO2, CeO2, ThO2. There were these common patterns that repeated. He predicted the existence of 3 undiscovered elements. If we go back to his table here, you see some blanks, right? And these here, Eka, these are ones that he predicted would be discovered. And he not only predicted that they would be discovered, he predicted what their properties were based on the properties of the elements around them. And here's his prediction for what he called Eka silicon. Eka is a prefix that means below, so it was below silicon on his table. These are the predicted values: color, atomic mass, density, melting point, etc. And then this was discovered years later. He predicted in 1869. It was discovered in 1886. It was named germanium, and his predictions are remarkably accurate. So we're going to talk about some of the patterns that we see in the periodic table. The first noble gas that was discovered was argon. If we go back here, here's fluorine, and then it jumps to sodium. But if we look at the periodic table, there's an element between fluorine and sodium. All of the noble gases are missing from this periodic table because they didn't know, people didn't know that they even existed. The first noble gas was isolated in 1894, isolated from air, and the others were discovered within the next 5 years. Once people got clued in that, hey, there's these gases out there that are elements, they found the others and filled in that part of the periodic table. It wasn't, though, until 1962 that someone discovered a compound that contained a noble gas. The noble gases are very unreactive. They don't interact with other elements. For a long time, scientists believed that they could not make compounds. In 1962, they discovered a compound containing a noble gas. But these elements, argon, neon, and helium, we still know of no compounds that contain those elements. So that makes the noble gases kind of unusual. So the periodic law concept is an important one. I'm not going to test you on names and dates, but I'm going to test you on ideas, and this is one of them, the periodic law. Mendeleev arranged them by increasing atomic mass, But a scientist later named Moseley found that it was actually the nuclear charge that was important. The atomic number was more important. Because if we arrange them by atomic mass, there are a couple of pairs of elements that are out of order. And so Moseley determined that it was actually the atomic number that was important. And so this is what the periodic law says. The properties of elements recur in a repeating pattern when arranged according to atomic number. So here's an illustration of this using some of the elements. So here's atomic number 1, 2, 3, 4. Here's helium, an unreactive gas. And we come over here, 8 elements later, we see another unreactive gas. And over here, 8 elements later, an unreactive gas. Right next to the unreactive gas is a soft reactive metal. Soft reactive metal. Soft reactive metal. There are patterns in the elements when arranged by atomic number that repeat themselves. So here's our modern periodic table with all of the elements, well, pretty much all the elements known. And I don't remember what I'm supposed to say about it. We'll probably jump back to it.